For the problem of dimensionality reduction, by far the most popular, by far the most commonly used algorithm is something called principal components analysis, or PCA. In this video, I'd like to start talking about the problem formulation for PCA. In other words, let's try to formulate precisely exactly what we would like PCA to do. Let's say we have a data set like this. So this is a data set of examples x in R2, and let's say I want to reduce the dimension of the data from two-dimensional to one-dimensional. In other words, I would like to find a line onto which to project the data. So what seems like a good line onto which to project the data? It seems like a line like this might be a pretty good choice. And the reason we think this might be a good choice is that if you look at where the projected versions of the points go. So I'm going to take this point and project it down here and get that. This point gets projected here, to here, to here, to here. What we find is that the distance between each point and the projected version is pretty small. That is, these blue line segments are pretty short. So what PCA does formally is it tries to find a lower dimensional surface, really a line in this case, onto which to project the data so that the sum of squares of these little blue line segments is minimized. The length of those blue line segments, that's sometimes also called the projection error. And so what PCA does is it tries to find the surface onto which to project the data so as to minimize that. As an aside, before applying PCA, it's standard practice to first perform mean normalization and feature scaling so that the features x1 and x2 should have zero mean and should have comparable ranges of values. I've already done this for this example, but I'll come back to this later and talk more about feature scaling and mean normalization in the context of PCA later. But coming back to this example, in contrast to the red line that I just drew, here's a different line onto which I could project my data, which is this magenta line. And as you can see, this magenta line is a much worse direction onto which to project my data, right? So if I were to project my data onto the magenta line and get a set of points like that, and the projection errors, that is these blue line segments, would be huge. So these points have to move a huge distance in order to get onto the get projected onto the magenta line. And so that's why PCA, principal components analysis, would choose something like the red line rather than like the magenta line down here. Let's write out the PCA problem a little more formally. The goal of PCA, if we want to reduce data from two-dimensional to one-dimensional, is we're going to try to find a vector that is a vector ui, which is going to be an Rn, so that would be an R2 in this case. I'm going to find the direction onto which to project the data so to minimize the projection error. So in this example, I'm hoping that PCA will find this vector, which I'm going to call U1, so that when I project the data onto the line that I defined by extending out this vector, I end up with pretty small reconstruction errors. I end up with sort of data that looks like this. And by the way, I should mention that whether PCA gives me U1 or negative U1 doesn't matter. So if it gives me a positive vector in this direction, that's fine. If it gives me sort of the opposite vector facing in the opposite direction, so that would be like minus U1. Let's draw that in blue instead. Right? Whether it gives me positive U1 or negative U1, it doesn't matter because each of these vectors defines the same red line onto which I'm projecting my data. So this is a case of reducing data from two-dimensional to one-dimensional. In the more general case, we have n-dimensional data and we want to reduce it to k dimensions. In that case, we want to find not just a single vector onto which to project the data, but we want to find k dimensions onto which to project the data so as to minimize this projection error. So here's the example. If I have a 3D point cloud like this, then maybe what I want to do is find vectors, so find a pair of vectors, and I'm going to call these vectors, let's draw these in red. I'm going to find a pair of vectors, so starting from the origin, here's U1, and here's my second vector, U2, and together these two vectors define a plane, or they define a 2D surface, right? Kind of like this sort of 2D surface onto which I'm going to project my data. For those of you that are familiar with linear algebra, for those of you that are really experts in linear algebra, the formal definition of this is that we're going to find a set of vectors, u1, u2, maybe up to uk, and what we're going to do is project the data onto the linear subspace spanned by this set of k vectors. But if you're not familiar with linear algebra, just think of it as finding k directions instead of just one direction onto which to project the data. So finding a k-dimensional surface, really finding a 2D plane in this case, shown in this figure, where we can define the position of a point in the plane using k directions. And that's why for PCA we want to find k vectors onto which to project the data. And so more formally, in PCA, what we want to do is find this way to project the data so as to minimize the sort of projection distance, which is the distance between the points and the projections. And so in this 3D example too, given a point, we would take the point and project it onto this 2D surface. We end up with that. And so the projection error would be, the distance between the point and where it gets projected down to my 2D surface. And so what PCA does is it'll try to find a line or a plane or whatever onto which to project the data to try to minimize that squared projection, that 90-degree or that orthogonal projection error. Finally, one question I sometimes get asked is, how does PCA relate to linear regression? Because when explaining PCA, I sometimes end up drawing diagrams like these, and that looks a little bit like linear regression. It turns out PCA is not linear regression, and despite some cosmetic similarity, these are actually totally different algorithms. If we were doing linear regression, what we would do would be, on the left, we would be trying to predict the value of some variable y given some input features x. And so linear regression, what we're doing is we're fitting a straight line so as to minimize the squared error between a point and this straight line. And so what we'd be minimizing would be the squared magnitude of these blue lines. And notice I'm drawing these blue lines vertically, right? That these blue lines are the vertical distance between the point and the value predicted by the hypothesis. Whereas in contrast, in PCA, what it does is it tries to minimize the magnitude of these blue lines, which are drawn at an angle. These are really the shortest orthogonal distances, the shortest distance between the point x and this red line. And this gives very different effects depending on the data set. And more generally, when you're doing linear regression, there is this distinguished variable y that we're trying to predict. That all that linear regression is about is taking all the values of x and trying to use that to predict y. Whereas in PCA, there is no distinguished or there is no special variable y that we're trying to predict, and instead we have a list of features, x1, x2, and so on up to xn, and all of these features are treated equally. So no one of them is special. As one last example, if I have three-dimensional data and I want to reduce data from 3D to 2D, so maybe I want to find two directions, u1 and u2, onto which to project my data, then what I have is I have three features, x1, x2, x3, and all of these are treated alike. All of these are treated so symmetrically, and there's no special variable y that I'm trying to predict. And so PCA is not linear regression, and and even though at some cosmetic level they might look related, these are actually very different algorithms. So hopefully you now understand what PCA is doing. It's trying to find a lower dimensional surface onto which to project the data so as to minimize this squared projection error, to minimize the squared distance between each point and the location of where it gets projected. In the next video, we'll start to talk about how to actually find this lower dimensional surface onto which to project the data.